Light is a wave of electric and magnetic fields. Sound is a wave of air pressure. According to quantum mechanics, all the particles in the universe have the properties of waves, including all the particles that we ourselves are made from. Therefore, to understand light, sound, and the very nature of reality, it is necessary to first understand waves. To understand the properties that all waves have in common, consider a wave traveling along a rope. The wave transmits energy and can encode information. Yet each individual atom stays pretty much in the same spot. When a wave reaches the end of the rope, the wave and its energy are reflected back. If the end of the rope is fixed and can't move, the reflected wave is flipped upside down. If two waves collide, they pass right through each other. When the two waves are on top of each other, they can momentarily cancel each other out. When the two waves are on top of each other, they can also momentarily strengthen one another. Here, the two waves strengthen each other where they intersect. Now suppose we have more than two waves. Now suppose we have an infinite number of waves. This wave is composed of an infinite number of waves that spread out in all directions. When added together, they form a wave that travels in just one direction. Let's consider what happens when this wave hits a barrier with a small hole. The waves behind the barrier are blocked. Only the wave behind the hole passes through. Since this wave no longer has the other waves to combine with, there is now nothing stopping it from spreading out in all directions. This is the reason why waves spread out when they pass through a small hole. Now suppose the hole is bigger. If the hole is bigger, then more of the waves are able to pass through. If the hole is small, the wave spreads out in all directions. If the hole is bigger, most of the wave keeps moving forward without spreading out. To understand why this happens, consider the pattern that forms when a wave passes through a large hole. The waves going to the sides often cancel each other out, whereas the portion of the waves going forward always strengthen each other. However, if the distance between the incoming wave peaks is much larger than the length of the hole, then the waves that pass through the hole strengthen each other in all directions. The wave spreads out when the distance between the wave peaks is much larger than the length of the hole. If the distance between the wave peaks is much smaller than the length of the hole, then the wave moves forward without spreading out. For this same reason, if the distance between the wave peaks is much smaller than the size of an object, the object will block the waves. If the distance between the wave peaks is much larger than the size of an object, the waves will go around the object. In the case of sound waves, the distance between the wave peaks is much larger than most objects we deal with. Sound waves can therefore go around most objects. In the case of light waves, the distance between the wave peaks is much smaller than most objects we deal with. Most objects therefore block the passage of light waves. This is the reason why we can hear things even if there is an obstacle in the way. We can't see things if there is an obstacle in the way. Some materials allow light waves to pass through. Although the speed of light through empty space is the same to all observers, light slows down when it passes through certain materials. The image is distorted because when a wave passes into a material where its speed is different, it changes direction. To understand why waves change direction when they enter a material where their speed changes, consider the following. If a wave enters the new material at a 90-degree angle, then it will continue moving in the same direction as before. If the wave enters at a different angle, then the left side of the wave will enter the material at a different time than the right side. White light is composed of all the different colors combined together. Each color of light is an electromagnetic wave with a slightly different frequency. In some materials, the speed of the wave does not depend on the wave's frequency. In other materials, the speed of the wave does depend on the wave's frequency. If white light enters this type of material, each color will bend at a different angle, causing the colors to separate in different directions. This is why sunlight passing into rain droplets can create a rainbow. Consider a case where the speed in the material we are entering is significantly faster than in the material we are leaving. If the angle is shallow enough, there will be a total reflection of the wave. This is how light stays inside fiber optic cables. Although waves sometimes reflect completely, there is always at least some reflection every time a wave transitions into a material where the speed is different. The greater the difference of the speed in the two materials, the greater the reflection. If the material we are entering has a lower speed than the material we are leaving, the reflected wave is flipped upside down. If we have more than one boundary, then there will be a separate reflection at each boundary. In the case of light waves, these types of double reflections occur at the surface of air bubbles and on thin films of oil floating on water. The two reflected waves can either strengthen each other or cancel each other out, depending on the frequency of the light and the distance between the two boundaries. Since the thickness of the bubble's surface varies from one spot to another, different spots on the bubble will have different frequencies of light strengthen each other or cancel each other out. This is why bubbles and thin films of oil sometimes have a rainbow appearance. If a wave is fixed at 2 points, it can vibrate like this. If it has more energy, it can instead vibrate like this. With even more energy, it can vibrate like this. Or like this. According to quantum mechanics, all particles are described by waves. The wave describes the probability of where the particle is located. If the particle is given more energy, the wave will look like this. As the particle loses energy to the surroundings, the wave changes. The probability of a particle being at a particular location depends on the wave's amplitude at that location. This means that in this case, the particle has a zero probability of being in the middle area where the wave's amplitude is zero. The particle somehow transitions from one side of the box to the other, without ever crossing the boundary in between. This means that this is not an accurate representation of how the particle is moving, and there is no accurate representation. Let's try to represent the particle moving in a different direction. As before, how the wave looks depends on the particle's energy. Now let's try to represent the particle moving in both directions. The wave describing the particle now oscillates in both dimensions. How the wave looks depends on how much energy the particle has in each direction. Now suppose that instead of moving in two dimensions, the particle is moving in all three dimensions. And instead of being bound inside a square box, it is bound by the charge of the nucleus of an atom. As before, there are a number of possible waves that can describe the probability of where the particle is located. These possible waves are what we call the electron orbitals of an atom. Each orbital corresponds to a specific amount of energy for the particle. All the atoms and particles in the universe behave this way, including all the atoms that we ourselves are made of. Waves are at the very heart of the nature of reality.